Hi there. In this video, we're going to be illustrating QGen's model verification capabilities. We're going to be showing it with two different kinds of models and at two different levels of analysis. At the lower level, we consider it essentially bug finding, designed for finding places where there might be something as simple as a divide by zero or some other relatively low-level problem in the code. We also are going to illustrate proof, model proof, where we will have a model which has a use of a Simulink assertion block, and we'll try to prove that the assertion remains true throughout the execution or simulation of the model. So our first example is going to be a simple speedometer model, and we're going to be looking for simple kinds of bugs. In this particular case, we're going to be finding a divide by zero problem. So here again, we have our model, and we're running in the Simulink IDE. And as before, we've seen there is this additional menu called QGen, and it has two options, build and verify. In this case, we're going to use verify on this model to try to find what problems might exist in it. And we're going to choose the bug finder mode, which is a little bit faster, a little bit simpler, and it does a somewhat lighter analysis on the model. So here we go. We're going to run it now. And in the background, it will be reading in the model, converting it into a form in which it can do static analysis, and then reporting on any problems that it finds with that representation that we use for static analysis. And it'll take a moment to complete. And if we look at the window, we'll see that there is a potential divide by zero problem. It says the divide by zero might fail, and it requires that this float signal value is not equal to zero. If we click on this underlined name, it will take us to the particular signal in the model, or the particular block which is reading in the signal. And here we have a check to see that here we have our divide by zero, and the danger is that the output of this division may fail because the input might be zero. So what we have to do is somehow prevent this input from being zero so the output doesn't end up being an invalid value. Now, there are various ways to do this, but the simplest is simply to check to see if this input is zero. Then we can replace it with a, let's say, the number 1, which will not allow for divide by zero. So let's shrink this window a little bit here. And rather than my actually editing this model, what I'm going to do is open up a different model, which is exactly the same as this one, except that it has some additional defensive coding to prevent the divide by zero. This is the new piece of code down here. Rather than having this output go directly into the input of the division here, we're now going to have it check to see if the value is greater than zero, then we'll pass it through. If it's not, then we'll pass in the value 1, and dividing by 1, of course, will simply leave the value unchanged. So now we're going to rerun the QGen model verifier on this fixed up model, and we'll verify that as a result of our change, we now have eliminated this particular source of potential runtime error. Again, it's reading in the model and turning it into a form in which we can do the static analysis of the model. And now we have seen that we now have no errors found by the verification tool. So that was our first example. And the next one is a slightly more complex example that involves a set of a cruise control system that uses a set of blocks to assert a certain characteristic of the model. And here's our cruise control model. And we have some assertion blocks, which we use to show the state of the system. Let's see. Here we go. Here's the overall model. This is a subsystem of the model. We can drill down. But in the overall model, what we've done is we've taken this subsystem, we've read the two signal inputs and put them into an OR block here. We've taken the output, and we are making certain that if you're either touching the brake or the clutch, then we don't want the cruise control to be active. So if we're pushing on the brake and the clutch and the cruise control is active, we never want that to be true. So the not of that should always be true. So this is how, using logical blocks and an assertion block, we can check to see if the logic within this subsystem operates as expected. And we could simply run the model and see if it died, but that might take a while. It might not always happen. It might be an unusual event. Often these things are. So instead what we're going to do is we're going to do a static analysis of the model. And we do that essentially in the same way, except that in this case we're going to use QGen, and we'll indicate that we're going to do proof, which does a slightly more intense model verification step. And now here we go. We're transforming this again into a form that allows us to analyze it more completely. And sure enough, we have gotten a concern that this assertion might fail. Assertion requires that you never have the case where you have the cruise control or the clutch and sorry, you never have the clutch and or the brake on and you have the cruise control on. So it's a little concerned that this might be a problem. So we can click on one of these to take us to that particular place. Here's our switch, and we're concerned that this might be generating the wrong output. If we look up here, somewhere in this subsystem there seems to be a problem. And if we drill down into the subsystem and we look at how it's structured, we can recognize that in the assertion block we were considering if the brake or the clutch was touched, then that should effectively turn off cruise control. But it turns out that there's an AND operator here. So this was sort of an off by one operator. This should have been an OR, because if either one of these is, if the driver steps on either the brake or the clutch, we want to turn off cruise control. So let's fix this. And again, rather than actually making the edit here, I'm just going to switch to a version of this which has an OR. And now we can see that here we have the cruise control. This is still the correct set of assertions, but now we have fixed a bug within the implementation which was using the wrong logical operator. So with this fix, we're now going to rerun the verification. Okay, now we're going to run proof, and here we go. And now this time we would expect to have no errors found. And as we see, no potential errors found. So with our fix to the logical operator, we see that the model verification tool is able to verify that now our spec corresponds to the implementation, both ORs, which is good. Thank you very much.